Okay, now is it visible to everybody?
Yes, sir.
Okay, so the ADC which we are looking, it is a successive approximation resistor type of ADC. So in this ADC, we have a op amp at the input and an inbuilt DAC inside of ADC only, and we have one n-bit resistor, and here we have one comparator. This is a RC timing circuit, and the CSH is a sampling and hold capacitor which is put inside of ADC. So what exactly acquisition phase is? Acquisition phase, there are actually two phases in ADC for conversion. One is acquisition phase and another one is conversion phase. So in acquisition phase, the goal is to charge your sampling and hold capacitor to the output of this amplifier, which is also there inside your ADC. So this all block actually it is embedded into your main controller only: amplifier, RC connections, comparators, and bit register and DAC. So this is just to show you an overview of how ADC works. Okay, so you basically have a sampling and hold capacitor, and this S1 actually, when it is turned off, your sampling and hold capacitor will charge to the output of this amplifier. So depend on what reference signal you are selecting here and what RC timing you have, this capacitor will charge to the value which is called as VSH. Okay, so basically this VSH will be V in plus minus zero point 0.5 your zero point 0.5 of your LSB. LSB means least significant bit. So you can say V in is your 2.6 volt. So plus minus zero point 0.5 of LSB, least significant bit and most significant bit, you know. So whenever you have any analog signal of 5 volt and you convert it into digital, so you have one MSB of that and you have one LSB of that. Let's say you have a 5-bit resolution of any ADC and you have a 5 volt signal. So whenever you have 5 volt signal and 5-bit resolution, it means there are 5 timestamps of that particular ADC that you need to convert. Like each voltage you will get at one step. So that like that will be 5 steps. So if you see the conversion, okay, in first itself it will be like 1 by 2 of your MSB, then you will see 1 by 4 of your MSB, then 1 by 8, 1 by 16, 1 by 32. Like this 5 steps will be there, okay, to convert your 5 volt into different voltage step. So that's what a resolution of LED is. So the zero point 0.5 of whatever least significant bit of that particular conversion will be there. Okay, so this capacitor is designated to settle at this particular value. So since this value of LSB is very less, because basically it is actually one particular voltage step when you are looking at the ADC resolution. So this is very less. So you can consider it equal to V in mostly. So V in is 2.6 volt. Okay. So this VSH is designed to uh, uh, so this VSH is basically voltage across this sampling and hold capacitor. So what this sampling and hold capacitor does is, whenever there is acquisition window of certain timing, this switch gets closed and your capacitor will gets on charging. So till the point like 19 nanosecond, 300 nanosecond, 1400 nanosecond, whatever. So those time, that is the time required to charge your sampling and hold capacitor to the output of this amplifier. Okay, so that time you need to give, which is by default it should be there, because this sampling and hold capacitor, if your ADC reference and everything is set, of course you need to put a particular acquisition time so that this sampling and hold capacitor should get charged to particular voltage. And once it is it got charged, this S1 will get open, and then this value of VSH will go into the comparator positive terminal. After that you have a DAC over here, inbuilt DAC over here. So depend on the resolution of your ADC, the DAC voltage steps will be selected, and that voltage will be applied to your negative terminal. So this comparator will compare 2.6 volt and whatever voltage step coming at your DAC, like 1 by 2, 1 by 4, 1 by 12 of 4.096. So then it will compare, and accordingly it will show output 1 or 0. If it is greater than this negative input, your output will be 1. If it is less than your negative input, your output will be 0. That's how any basic ADC works. Okay, so that phase is called as a conversion phase. So acquisition phase is something which is used to charge your sample and hold capacitor, and conversion phase is something which actually gives you output and it stores into this n-bit resistor. Okay, so n-bit resistor then gives you output. If it is a 5-bit ADC, it will give you from D0 to D5, D4, like that. If it is a 12-bit ADC, from D0 to D11. So there will be 11 bits which will convert your, which will be useful for converting your input voltage. So whatever analog to digital converter, what we are doing is we are taking any analog signal which is of continuous nature and we are discretizing it. So whatever sampling frequency we have of that particular ADC, okay, that will decide our interrupt service routine call into our algorithm. Okay, and then your ADC result will get stored. So you need to have a maximum sampling frequency It should not be more also, because your ADC main clock operation is limited to 50 megahertz maximum frequency. So your sampling frequency must be less than that. So if your 10 kilohertz is the signal, you can put your sampling frequency up to 1 megahertz or 2 megahertz. Okay. So we'll see in program how that is programmable. So this is how the conversion of ADC happens in a basic way. Okay. So this we missed yesterday. Then we saw if your ADC is 12 bit, so basically 2 to the power 12 is 4096. And if your ADC input is, let's say, 1 volt now, and V reference low is 0 volt, so V reference low will be 0, 0. So 1 by V reference high, if it is 3.3, this is selectable. Okay, you can select reference as per your choice, but certain registers are there in order to give you external reference for your ADC, so that you can improve the resolution of your ADC. Okay, so by default it is set at 3.3, and your ADC input is 1.1 volt, and if it is 3.3, then 1.1 divided by 3.3 into 4096, that will be your analog to digital conversion result. So every voltage step, okay, it will get converted into digital data, and depend on the sampling frequency, those many samples will get stored into your ADC. Okay, so that's how a signal conversion basically happens. And we saw yesterday that for any single ended ADC input, okay, channel selection defines which pin to select, ADC input 0, 1, 2, 3, 4. Okay, and from any of the, and if you select any one of this ADC input, you can just go to, your basic diagram. There you have this pin configuration. So from here you can see these are the certain ADC input pins, J7, 60, 70, 65. Okay, these are assigned as ADC input A5, A4, A1. So you have to select from this one. Okay, so this I have told you already yesterday how to select this. Okay. Then you have a trigger selection. Trigger selection in the sense to select the sampling frequency of your ADC. This trigger selection is required. So we saw yesterday that if we are choosing, trigger selection equal to 10, what will happen is you will be choosing EPWM3 from here. ADC trigger 10 is EPWM3. So your ADC start of conversion signal will be generated by EPWM3. Okay. And we'll see how do we generate that. So is my screen visible to you all?
Yeah, Tushar.
Okay, I'll try to focus on Word. Let's see if it is okay. It will be disaster, I guess, but I'll try. Okay, I guess it won't be possible onto this slide. I just wanted that it should be visible for you guys. Okay, so we're looking into ADC. Okay, one more thing I can do is I can copy this. Yeah, so now it will be a little bit clear, right? So since you can see from here, I have defined certain function. Okay, so in order to configure your ADC, you need to have two main functions. Okay, so this is the first function. Okay, so this is the first function that you need to have. So in this function, what you are doing is you are configuring ADC. So whatever basic signals of your ADC, like which channel to select, which start of conversion signal to select, okay, that will be there into this particular function, void configure ADC. Okay, so it is a predefined function and you have to configure your ADC into this function only. Okay, so this is the first function which belongs to ADC configuration. Then you have second function. This is also a predefined function, just like initial EPWM1 example. Okay, just like this predefined function, this is also a predefined function. Okay, so into this function, you can configure your EPWM. So EPWM, we are configuring for start of conversion signal. Start of conversion signal, we decide the sampling frequency of your ADC. Okay, and sampling frequency of your ADC will decide the running rate of your ISR. So 1 by sampling frequency will tell you what is the running rate of your ISR. That is, after, if it is 10 megahertz, 1 by 0.1 mega, that will be equal to, let's say, some nanoseconds. So after that nanoseconds, your ISR loop will run. Just like in configure, if CPU timer we saw, okay, when our EPWM ISR was running, we can program it using ET selection register. Okay, just like in EPWM we saw using, okay, it's not there into this example. So I hope everybody remembers that ET selection so that I don't need to tell you again. Okay, ET selection is a event trigger selection. I will tell you once again in case if you forgot. Yeah, so this was I was talking about. Okay, so this ET selection, interrupt selection. From here we select when to trigger an interrupt. Okay, for EPWM at counter 0 we are triggering the interrupt whenever our counter start counting from 0, and this is interrupt enable, and this is third event, like after 3 triangles every interrupt will repeat. Okay, so just like this, your ADC interrupt, when it will come, it will come after, 1 by 50 megahertz. Okay, so your ISR will run after 1 by 50 megahertz of time. Then you have DAC. Okay, so this is to configure your DAC, and in order to see your analog to digital signal that you have converted, whether the same signal you are getting into the board or not, for that you can use DAC. Like let's say you have signal inside and you want to see it on the oscilloscope, whether same signal is there or not. So that digital data you can as well convert into analog form, and you can see the output onto your oscilloscope. Okay, so whatever signal you are converting, whether it is accurate or not, okay, that you can detect with the help of DAC. We'll see how to do setting for that DAC as well. There are other registers, and I did not want to confuse you with ADC, so I'll take it later. Okay, then you have ADC EPWM. Okay, so this particular function is also there. So 3 functions we need for ADC. One is for configuring ADC. Another one is to configure EPWM for any start of conversion signal. And then how we are triggering our ADC with EPWM. How to trigger your ADC with EPWM. Okay, this is for your void ADC EPWM. Okay, and this ADC ISR I told you, it will come after 1 by of sampling frequency. Okay, so in this ADC ISR, what we do is we store all the results. Results of your ADC conversion. So whenever ADC conversion is complete, a end of conversion signal is generated, and that end of conversion signal will help you to store your data into the register called as ADC result register. Okay, so there will be something called as ADC result register. So whatever conversion data, that will be saved into this ADC result register. Then we have 2 PWMs here, 1 and 3. Okay, 1 will be unnecessary, only 1 PWM will be using. So these are certain variables over here. Okay, I will tell you what it is. Before that, I need to tell you about the settings of ADC first. Then we'll talk about other things into this code. Okay, so this is to configure ADC. Okay, this is to configure ADC. So in order to configure ADC, I already told you the first function, which is to configure ADC, is to select the ADC configuration. ADC configuration into the channel or pin on which you are converting. Pin for conversion. So this is useful in order to see pin for your conversion, or select which EPWM is responsible and all. Okay, so we'll see every instruction. What does it mean? Okay, So from here you can see this prescale is there in order to select your ADC clock frequency, like main ADC operation. As I told you, like EPWM also operates on its main clock. Okay, like 100 megahertz is the clock frequency of your ADC. So similarly, your ADC also has some clock frequency, as it is also an independent peripheral. So ADC has a maximum clock frequency of 50 megahertz, and when you divide your prescale as 4, it will operate at 50 megahertz. Okay, so you can see from the register itself in technical reference manual, if you go to ADC CTL2 and you will see the bit prescale, it will be written here there that if it is 0, then it is divided by 1. If it is 2, then it is divided by 3. If it is 4, then it is divided by 4, something like that. Just like in HSP clock division, main clock division, while selecting TB clock, we saw na TB clock, it was equal to what? It was equal to EPWM clock divided by HSP clock division into main clock division. So we saw that selecting these particular values will decide ki how much. If your HSP clock division is 000, it will be divided by 1. Clock division 000, it will be divided by 2. Like that we saw in register. Similarly, this prescale is there. So by putting 4 here, you are setting ADC clock divided to certain value, okay, which will give you highest clock frequency of 50 megahertz. Okay, you have to put it 4 over here. Then you have a resolution. Okay, so this is to select your ADC resolution. So we are selecting 12-bit resolution by putting 0. If you put 1, it will be 16-bit resolution. So basically we are going for single-ended conversion. So resolution available to us is only 12-bit. So that's why we are selecting 12-bit resolution. Okay, then this is a signal mode. In order to set your connection into the to confirm that your conversion should happen in 12-bit mode only, you select 0 in front of this signal mode resistor. Okay, so then you select always input pulse position to late. Okay, you don't have to worry about these two instructions. You keep it as it is. If you do not understand it, you keep it as it is. Okay, do not change it. It will not make much of the difference. And this ADC power is to set up power up is to power up your ADC, and this delay of 1000 microseconds is necessary in order to allow your ADC to get power up. Okay, so these three instructions you do not change at all. Okay, you keep it as it is. Okay, don't worry, I'll give you this code, okay, so that you can configure on your own. Then you have a EPWM. So into this EPWM, what you are doing is you are configuring your PWM in order to generate a particular pulse, and that pulse will be a start of conversion signal. And start of conversion signal is what? It will decide the sampling frequency of your ADC. And what sampling frequency of ADC will do? It will tell you what samples you are counting at and at what rate your ISR or interrupt service routine will get served. Okay, so you are basically you are freezing the counter here. Okay, once counter will start counting, you have to freeze the counter into this process. Okay, so whenever you are configuring EPWM for ADC SoC, you need to first freeze the counter. Okay, so you freeze the counter means you stop the counter running. Okay, after that you select your HSP clock division to certain value, whatever time based clock you want to set. Just like normal EPWM configuration, this block is there. Okay, TBPRD you are setting and HSP clock division you are setting, so that you are setting the value for your TB clock. And just like your PWM frequency is there, okay, like that only this particular thing will happen. But you have another thing here, that with the help of interrupt selection register, we are selecting when to generate our start of conversion signal. Okay, so I have selected SOC period on first event in the sense, after the first triangle itself, it will generate a start of conversion signal. Okay, so this is to enable the SOCA enable. SOCA selection is when to generate your start of conversion signal. When to generate your start of conversion signal is what? Basically, here you're not setting anything like, acquisition qualifier. Action qualifier is not there, in which you are setting set and clear. Okay, like that you are not setting the pulse here. You are selecting a SOC. So whenever you are selecting a start of conversion signal, you are selecting to turn it on 0. Okay, and then period it will reset. Okay, so basically when it is a up counter on 0, the pulse will start. On period it will reset. Again on 0 it will start. Again on period it will reset. So that's how the frequency of PWM will be there into this one. Okay, so every first event means after every one triangle, a start of conversion signal will get generated. Okay, and you are selecting SOC on a period match. you're selecting SOC on a period match in the sense whenever your time base period value has reached, your start of conversion signal will get generated. Your counter is counting from 0 to 2000. Okay, so based on the period match, okay, it will start converting. So whenever you have 2000 counts, your frequency of any PWM will be 50 hertz, 50 kilohertz. Okay, this we are selecting with the help of formula. You know the formula for this, right? I'll tell you once again. So TPWM is equal to 2 into TBPRD into what was their time for TB clock. This TB clock is decided by EPWM clock. As I said previously, TB clock is equal to EPWM clock divided by clock division into HSP clock division. Okay. So it will be something like this. Okay. So and your EPWM clock is what? You already know your EPWM clock. It is at 100 megahertz. Okay. This is how you select your frequency of your start of conversion signal, which will decide the sampling frequency of your signal. Okay. Then you are selecting that SOC to generate on period match. Okay. Period match in the sense whenever your counter will reach period, okay, your pulse will be turning on from 0 to period, and after that it will get reset. Okay. It means that. So this is the selection. With the help of event trigger selection, you are selecting SOC. Event trigger pre-scaler resistor is to select the period after which you need to generate SOC. So SOC is a start of conversion signal which is deciding the sampling frequency. Okay. Then this DAC we'll see later. This okay, I'll tell you about DAC as well. Basically, DAC is just converting your analog signal into digital signal. So with DAC control resistor DAC CTL, you're selecting DAC reference to be at ADC. Like whatever ADC reference 0 to 3.3 volt, okay, that reference is only belonging to DAC. It means that if you're putting 10 here, if you're putting certain other things, okay, you can as well have a external reference for DAC, like whatever voltage you want to put, but it will not be more than 3.3 because that is the maximum allowable voltage that you can put into your board. Okay, so by default it is at 0 to 3.3 volt. Then load mode you have to select 0, like load on the next system clock cycle. You have to load a DAC with certain values so that you are seeing output onto your oscilloscope. So for that you are saying that when you're putting 0 into the load mode, you're actually loading it onto the next clock cycle of your system clock, which is operating at 200 megahertz, so that your DAC will help you to convert the result faster into analog and you can see it on the oscilloscope. Okay, this is for mid range. So if you put some value over here like 800 or something like that, what will happen is your DAC output will be offset by that particular value into the output. So I recommend you to put it at 0 if you want your signal to start at 0. If you want your signal to start at midway, okay, from the oscilloscope, like offset from certain 0 value, you put some value over here 800 or something. Okay, if you it's not at mid range now, okay, it's at 0 only, but if you put 800 over here it will be mid range or something. Okay, so based on the DAC resolution I'm setting the mid range. Okay, if your DAC resolution is 8 bit and it is 1023, so half of that, okay, if you set that value into this particular DAC values register, your DAC output will be offset. Okay, then you have DAC output enable, like you are enabling the DAC. So basic understanding of DAC and ADC is that you need to understand it will take only positive signal into single-ended conversion mode ranging from 0 to 3.3 volt. Okay, and it cannot output a negative signal as well. Then you can see from here your ADC EPWM. Okay, so this function is to select your channel on which you are converting. So three functions we saw. Basically, first we saw was configure EPWM. Sorry, configure ADC, like selecting clock frequency and everything for ADC. Then configure EPWM in order to generate start of conversion signal. Then we saw DAC, how to see output with DAC. Then we saw how to select ADC SOC on particular channel, like what channel you need to convert. So for that, there is a predefined function known as setup ADC PWM. So these three instructions I have explained before. This is to select your acquisition prescaler window. So you can see sample window is 100 system clock. 100 system clocks in the sense 100 into 1 divided by your system clock frequency is 200 mega. So this time will be there for acquisition prescaler window. Okay, it means that if you're putting acquisition prescaler as 14, it means your sample window will be 100 system clock. It means 100 into 1 by 200 mega. So this by default is set to 100 system clock with 14. Okay, so you don't need to change it. That is the minimum time required to charge your sampling and hold capacitor that I told you previously. Then you have a trigger selection. So from here we are triggering on EPWM2. So if I'm putting 7 into trigger selection from my configuration, I can see if I'm selecting 7, okay, into trigger selection, if I'm selecting 7, it means I'm triggering on EPWM2. So ADC start of conversion signal will be generated by EPWM2. Okay. Then you have a ADC ISR. So this was about that. Okay. Now these three I have explained. Then okay, this is setting for ADC interrupt. Okay, this you need to do. So this is what is telling you that whenever any end of conversion signal is happen, end of conversion signal means ADC has stopped converting now. Your signal has got converted. Okay, so one cycle or after certain cycle of conversion, your end of conversion signal will generated, and you are selecting to generate interrupt on that particular end of conversion signal. So this instruction means that you are selecting interrupt, okay, to generate on the end of conversion of your start of conversion signal. Then this is to enable your interrupt flag, okay, and then your interrupt flag should be cleared. So this ADC interrupt flag clear bit is for clearing the ADC interrupt. Just like in interrupt ET selection register, we saw how to select an interrupt. Similarly, this instructions for that only. Okay, but here you can see you cannot tell that when your period is there in order to generate ADC interrupt. So that period I already told you, it depends on sampling frequency. So 1 by sampling frequency your ADC ISR will run. Okay, then into this code, okay, whenever your ADC ISR is running, you can see this is a register which is ADC A result register, ADC result 0. So this registers will tell you, this register will tell you that if you're channeling onto ADC A, okay, there are three ADC, ADC A, B and C. Okay, so ADC A result has to store in which register? ADC result register. Why 0? Because I'm selecting A0 pin to convert on. Okay, ADC input A0 I'm selecting to convert on, and that I saw from here that SOC will convert on pin A0. Okay, that's why result will be also on 0 pin. So that result I'm storing with the help of that ADC result register. Okay, and then I'm scaling it in order to see particular voltage. So I'm putting it into the variable T. So I'm scaling it into 3.3 divided by 4096 since it is a 12-bit ADC, and reference is from 0 to 3.3. So for every ADC, I need to see what is the voltage. For that voltage, I'm putting it as T over here. Okay, and this is for generation of sine. So this code basically what it does is generate sine inside, and when I'm multiplying this T to my reference, which is a sine wave, and when I vary the pot, actually the sine magnitude will change, and that I will observe onto the DAC. So into the DAC, I have stored that particular value. So from here you can see into DAC values register. This is the output of the DAC. Okay, so I have written here DAC B. So I'm selecting DAC B for configuration. Okay, and in this one I'm putting AI into 3.3 into 4 divide by 3.3 into 4096. So this will give me analog input obviously from digital data. So whatever my digital data is stored into this AI, okay, that I'm trying to convert it into, sorry, whatever analog data is stored into this AI, because T is an analog signal. I'm converting it into analog again, because once it is into digital, you can see I'm scaling it with 3.3 multiplication. So it means I'm getting an analog value into T. So this analog value I need to convert into digital before feeding it to DAC. That's why I'm dividing it by 3.3 into 4096 again, so that it should get converted into digital. So let's say if it is 3.3, okay, so 3.3 by 3.3 into 4096, it will be 4096. So DAC value will be 4096 in that case. So I'm giving DAC to 4096 and DAC will output me 3.3 volt in the oscilloscope. Okay, so this is related to ADC configuration. Okay, now so you can see from here I have selected DAC B. for configuration. Okay, that's why I'm seeing all my results on DAC B only. Okay, so this is how you configure DAC for any particular module. Okay, and then I was comparing with PWMs and all, so you don't need to worry about that. So this was about the ADC code. Does anybody has any difficulty into this one? Any doubt till now? Does anybody has any doubt? Am I audible? Hello. So, are you there? Am I audible to everybody?
Yeah,
Hello.
Tushar, you are audible.
Okay, so is there any doubt till this point? I guess no doubts. Okay, so we can move further. Mm, so, if I play any video, will it be audible to anybody?
Yeah, sure.
Okay, if I play any video, will it be audible to people? I'm asking that.
Yeah, I'm saying that it will be audible.
Okay. So I want you guys to watch one video. Okay, right now, okay, let's not watch it now, but I'll post the link. There is one video on TI website. Okay, you can see this video. This video will actually well demonstrate what is an EPWM module is. So I request you all to go through this particular video. Okay, once I have explained you, once you watch all my videos, you can go through this video. So it will give you clear overview ki what EPWM module is. Okay, so you can watch later as well. Now I have to explain you about the crossbar. Okay, so what is a crossbar is, okay, so the crossbar basically means it is the routing your signal. Like there are three types of crossbar. Routing your signal in the sense, I will give you an example first. First, you need to understand there are three crossbar basically. One is input crossbar, another one is output crossbar, and the third one is EPWM crossbar. So basically, whenever you have input crossbar, it means that you are routing your signal into the board, inside the board. Okay. And when you have output crossbar means you are routing your signal from out to the board. Like if your signal is there into the board, you want to see on the output just like that, then you can use output crossbar. And EPWM crossbar, you take your any signal and it brings into the EPWM module. So EPWM crossbar is to bring your signal into the EPWM module. Okay. So this crossbar is necessary in order to understand the routing of your signal. So let's say what does exactly routing means. Let's say your certain, uh, okay, I will explain this with presentation. Let's say you have a EPWM signal, okay, that you are generating onto certain pin. Let's say GPIO 0. This GPIO you are generating an EPWM signal. Now you want to observe the same EPWM signal onto GPIO 12. You will say, sir, how is it possible to see the signal on GPIO 12? If we are modeling GPIO 0 as EPWM, we can see only on that pin, whatever EPWM signal is. Yes, you are correct. But there is one more thing, okay, which is called as a crossbar, which helps you to see your EPWM signal onto the other pin. And that particular thing is called crossbar. So what I will do in crossbar is I will assign GPIO 0 as an input crossbar. Okay, so basically what I am doing is I am internally connecting a wire in between these two. I am internally connecting a wire in between these two so that whatever signal is there onto GPIO 0, I can see that on GPIO 12. So for that, I need to configure GPIO 0 as an input crossbar and GPIO 12 as a output crossbar. Okay. So once I will select this as an input crossbar and output crossbar, what will happen is I will be able to see my EPWM signal onto GPIO 12, which is there on this GPIO 0. Or let's say J740 this pin is, I can see it on J780 as well, the same signal. Okay, so in this way you can route your signal. So it is not possible from outside to do it. So internally they have given some connection. If you want to reflect your EPWM signal onto other GPIO pin, you can as well do that. So with output crossbar, what you are doing is you are taking your signal out of the device from GPIO 12, and you are putting the signal, EPWM signal, into the device with the help of GPIO 0. So this is what crossbar means. Okay, routing your signals. So if you see your input crossbar, the configuration is something like this. Okay, I'll just copy this. So in this example, okay, what I am doing first is I have initialized a function which is epwm 12. Okay, so now what I have done is, as per the rule, I have enabled the clock of epwm 12 module. Sorry, this is to divide the clock of EPWM, peripheral clock division. So if I am dividing it by 2, my clock frequency will be 100 megahertz only. If it is 1, then it will be 200 megahertz. Okay, but it does not mean that your EPWM will operate correctly, because by default we already saw our type 4 EPWM module has clock frequency of 100 megahertz. Okay, so by default you assume like that, you do not use this instruction. Okay. After that, you are enabling the clock of EPWM 12 with by selecting one, which is peripheral clock control register 2. So in this control register 2, you are selecting EPWM 12 to operate. Okay. Now you can see from here is you have selected GPIO 22. Now, I told you before, there are two muxes. One is Gmux and AMux. So from Gmux, you can see pin number GPIO 22 you have selected. Okay, so 0 to 15 was belonging to mux 1, and 15 to 30 was belonging to mux 2, right? So I'm selecting mux 2 and I'm selecting GPIO 22 here. But you can see I'm selecting Gmux as 1. Whenever I'm selecting Gmux as 1, means I have to go into EPWM, I have to go into GPIO and peripheral muxing and see what does that mean. So if I go to GPIO, so you can see from here, if I'm selecting Gmux as 1, means this block, and I'm selecting normal mux to be 1. Okay, from here you can see I'm selecting normal mux A mux to be 1 and G mux to be 1 for GPIO 22. What does that mean? It means that pin number GPIO 22, which is this, and I'm selecting this pin 01 and 01. It means I'm selecting EPWM 12A. Okay, so what I'm doing is I'm assigning this pin GPIO 22 as EPWM 12A pin, because I'm selecting Gmux to be 1 and normal mux to be 1. So in this way, my EPWM 12A is selected. Okay, so I'm assigning GPIO 22 as EPWM 12A. Okay, now, so this is to assign GPIO 22 as EPWM 12A. Okay, from peripheral module. Okay, now I have select input 1, input crossbar register, input 1 select I have selected as 22. So input 1 select, if I select 0, it means I'm selecting GPIO 0. If I'm selecting 1, it is means GPIO 1. If I'm selecting 22, means I'm selecting GPIO number 22 as an input crossbar. Okay, so from here, if you go and see, so from here you can see this is a basic crossbar configuration. Okay, so into this crossbar, you can see that your signals are routed from input to output, and certain signals are routed from EPWM. So from EPWM, you can as well route your signal to EPWM crossbar, which are also the trip signals. Okay. And then you have certain external synchronization signal, external interrupt signal as well. Okay. And these inputs can also be connected to eCapture module. Okay. eCapture will actually capture, give you a pulse on the detection of any edges. If you want to detect rising or falling edge, so eCap will give you a signal onto detection of that edges. So eCapture module is used for that, or to measure any frequency of any clock signal. This is eCapture is useful, frequency or time speed calculation. So from here you can see you have an input, it is connected to output crossbar. So input 1 is connected to output 1. Okay. Now if you go to this one, you can see input 1 is connected to EPWM trip zone, EPWM crossbar or output crossbar, and we are connecting it to output crossbar. Okay. Now so you can see from here, for input selection, if you select from GPIO, if you put 0 into this register input 1 select, you will select GPIO 0. If you are putting 22, you are selecting GPIO number 22. Okay, so this was about input 1 selection register. Okay, so we are selecting GPIO 22 as an input crossbar. Then what we have is a output 1 mux 0 to 15 configuration. So mux 0 to 15, okay, from mux 0 to 15, we are configuring mux 1. If you want mux 2, then it will be from 15 to 32. Okay, like that. So output 1 mux we are enabling, and we are selecting output crossbar configuration to add GPIO 22. How I am deciding that? I'll tell you. Let's say I have a GPIO 24. Okay. So from normal mux, I'm setting GPIO 24 as 1. So what does it mean if I'm setting GPIO 24 as 1 means? If you go to this pin and if you see GPIO 24, and if you are selecting GPIO 24 as 1, okay, 1, you can see your GPIO 24 is configured as output crossbar. Okay. So what does it mean? Your GPIO 24 has an output, okay, which is routed from GPIO 22. So from GPIO 22 to your output is connected to GPIO 24, because GPIO 22 is the input crossbar and output crossbar is GPIO 24. Now how do I enable output crossbar? So I'm enabling with the help of this register, output 1 mux 0 to 15 configuration. Mux 1 I'm selecting to be 1. Okay. So if you go into the technical reference manual and if you see this register, I was saying is, if you see this register output 1, now is it visible? So
Yes, Tushar.
okay, so you can see output 1 mux 0 to 15. So this register is enables you to select from mux 0 to 15, and you can see from here, if you select into this register value 1, you are selecting input 1 for connection. Okay, if your value is 2, you are selecting input 2. So since we are configuring input 1, from this one you can see you are configuring input 1 select. That's why we are selecting that particular register. Okay, so from we are within the reach from 0 mux number 0 to 15 because we are selecting mux 2. That's why this output 1 mux is from 0 to 15. Okay, so it is like that. And why it is output 1? Because we are selecting input 1. So input 1 should be connected to output 1, input 2 should be connected to output 2. So this way you can route your signal, which is GPIO 22 onto GPIO 24. Onto GPIO 22 you are generating a